Hello dear students. In this session we are going to solve a numerical on strain energy. In this question, using Castigliano's theorem, obtain the deflection under a single concentrated point load applied to a simply spotted beam as shown in figure. EI is given to us. So in this question, we have to apply the Castigliano's theorem, right? You know that this is a strain energy theorem. This is the theorem. Using the strain energy, we have to find the deflection. We can find the deflection of the beam using this theorem. So using Castigliano's theorem, we have to find the deflection under a point load. Point load is given to us, that is 60 kilonewton, which is applied at this distance 1 meter from the right end. And the EI part of the beam is also given to us. The product of modulus of elasticity and moment of inertia is given to us, right? So let us solve this problem using strain energy method. In this question, we are given with a simply supported beam of length 4 meter at which a 60 kilonewton load is applied at 3 meter from the one of the end. Simply supported beam is there, and we have to find out the deflection under this load 60 kilonewton, right? What is the deflection under this load, right? We have to find out the deflection under this load. This is the deflection, right? Say it is YC or delta. We want to use the Castigliano's theorem, in which we have used delta. So that's why I am using delta here. In theory we have used delta, so that's why. So we can apply here the Castigliano's theorem to find out the deflection under the load 60 kilonewton, right? So what is Castigliano's theorem? What is Castigliano's theorem? Castigliano's theorem. So what is Castigliano's theorem, right? So in Castigliano's theorem, the deflection or deformation under a given load, suppose this is the load and this load is suppose W, under a given load is given by the partial derivative of the strain energy stored in this bar, complete bar, strain energy stored in complete bar with respect to the load, this load, that particular load, right, under which we want to find out the deflection, right? So this is the Castigliano's theorem, right? And the strain energy in case of bending moment is given by, you know, that we have derived earlier, that this is given by m square dx upon 2ei, right? So m square dx upon 2ei, this is the strain energy stored. So when we partially derivate it with respect to load, what you will get, that we have already done this, that this will be given by the derivative of m square will be 2m, 2 to 2 cancel. So what you are getting is, as m by ei, go to the theory lecture, m by ei, differentiation of m square, right, 2m, 2 to 2 cancel, and del m by del w multiplied by dx, right? So this is a deflection under a given load W. Now before we proceed further, first find out the reactions RA and RB. How to find out RA and RB? First we have to find out this thing, right? So for finding RA and RB, what we can do is, we can apply that sigma m moment about any point, say A, that should be equal to 0. So this implies sum of all the moments about A is equal to 0. RA, the moment of RA is 0. The moment of this 60 kilonewton, so this is W, multiplied by the length, this is 3 meter, minus RB multiplied by this length 4 meters. So this will come out to be, RB will be equal to 3W by 4, right? 3W by 4. This is RB, right? And if we find out in magnitude, so you will get RB as 3 times 60 by 4, right? So this will come out to be 45 kilonewton. 45 kilonewton. We are using in terms of W because we have to differentiate here with respect to W. So that's why we are using 3W by 4 rather than 45 kilonewton. So you can write here 3W by 4. It will be easy to differentiate in that case, right? Now what is RA? For RA, we can find out sum of the vertical forces should be equal to 0. So RA plus RB, these are the upward forces, that should be equal to W, the downward force. So from here, RA can be found out as W minus RB. So this is W minus 3 W by 4. So this will be W by 4. So RA will come out to be W by 4. This is RA. And in magnitude, if you want to find out magnitude, that will go to 60 by 4, that is 15 kilonewton. But we are keeping it in terms of W because we have to differentiate with respect to W, right? So RA is W by 4 and RB is 3W by 4 and W is the load applied. Now we can take a moment about any X section, say X section we are taking here between A and C. So now we have to use bending moment here, but the problem is that the bending moment is different for AC and different from CB. So we have to divide it into two sections. One bending moment for AC and another is for CB, and the deflection formula, this equation will be valid. One for AC, which is 0 to 3 meter. If I am taking 0 from here, from left side I am taking 0 to 3 meters, and then again integrating from 3 meters to 4 meters, right? So then we will get the total deflection under a load of W, right? So now we can divide it into two parts. One is between A and C. So if I divide it into two parts, bending moment to be divided into two parts. This is for AC and here it is CB. It is valid for AC, it is valid for CB. What is the bending moment? Mx. When I am taking a section here, Mx. This is W by 4 multiplied by X. So this is W by 4 multiplied by X, right? None other force is there. So this is only one force, reaction is there. So W by 4 multiplied by X. This is the bending moment which will be used here, right? And differentiation of bending moment with respect to W is required. So what is del M by del W? So that will come out to be differentiated with respect to W and you will get X by 4. X by 4. So these two quantities we have obtained, bending moment and partial derivative of bending moment with respect to W, which will be used here in this equation. Suppose this is equation number 1. Now for CB, this part of the beam, we have to take another section at a distance X from the free end, from the one of the end, so simply suppose. And what is bending moment? So for CB, take a moment section X and find out the bending moment here. That will be sum of all the moments. So moment of W by 4 and W. So W by 4 multiplied by X minus W multiplied by this distance is X minus 3. X minus 3. So this is the bending moment. This is the bending moment for this part of the beam, right? So this will, if I further solve it, you will get it as, this is W by 4 minus 1. So this will be, this will come out to be, is it okay? W multiplied by X minus 4, right. So 1 minus 1 by 4, this is 3 by 4. So this is minus 3W by 4 X plus 3. This is the bending moment Mx, valid between C to B, right? And we need partial derivative. So del M by del W for this part will be equal to differentiation of this. So that will come out to be minus 3 by 4x. Minus 3 by 4x, right? So this is the two parts of this question, right? So first we have find out the mx at this part, which is W by 4 into X minus W times X minus 3. So this is 1 minus 1 by 4, this is 3 by 4. So this is minus 3 by 4 Wx plus 3. So this differentiation of this, partial derivative of this with respect to W will be equal to minus 3 by 4 X, right? So this is the equation we have obtained. Now what to do? What to do next? Put these values in this delta. So because the strain energy is the total strain energy is the total strain energy with respect to the load at which deflection is required. So we need to use the entire beam now, right? So delta will be equal to m by ei, m by ei, del m by del x, del m by del w into dx. From first, from suppose we are taking 0 here and up to 3, from a to c, from a to c, which is 0 to 3, right? And plus m by ei, del m by del w dx from c to b, right? So what we are getting is, the delta will be equal to m. The m value is known to us, that is wx by 4. So, and it is valid from a to c. A is 0, this is 3. We are taking a 0a and 3 meters is a c point, right? So m is known to us, that is w by 4x. So this is w by 4x. ei is there. Del m by del w is known to us, that is x by 4 dx, plus from c to b, c point is at 3 meter, b point is at 4 meter. So from 3 meter to 4 meters, m by ei, m is this much amount, that is m is minus 3 by 4 w plus 3, this is m, upon ei into del m by del w, which is this value, that is minus 3 by 4x, this is del m by del w, multiplied by dx, right? So this value we have obtained, right? We have to further solve it, and I am erasing this part. So delta will be equal to the constant things can be taken out and other things will remain inside, the x terms will remain inside. So this will be w by 16 ei, integration of x square dx from 0 to 3. So further, this is the first term, this term. Now second term. In second term, we will get this multiplied by this wx and then this multiplied by 3. So what we are getting is, we will be getting 9 by 16 ei and w, right? So this is plus 9w by 16 ei and then x square dx from 3 to 4 meters. And then again third term, again when 3 by 4 multiplied by 3, so we will get 9 by 4 minus 9 by 4 ei integration of x dx from 3 to 4. This we are getting, right? So once we are getting 9 by 16 and again we are getting 9 by 4 ei x dx, and here we are getting x square dx, right? Now this is simply integration, we can solve it by integration. So delta will be equal to w by 16 ei, integration of x square is x cube by 3 from 0 to 3 plus 9w by 16 ei, integration of x square is again x cube by 3, but the limit is 3 to 4, minus 9 by 4 ei, integration of x is x square by 2, limit is 3 to 4, right? So finally you will get w by 16 ei, this will be 27 by 3, 27 minus 0, so this is 27 by 3 is 9, so this will be 9 w by ei plus When you put it here, this will be 9W by 16 EI multiplied by, once you will put the 3, so you can take this 3 out, this is 48, and you will get 4 cube minus 3 cube minus 9 by 8 EI. Once you will put the 4 square minus 3 square. So finally you will get delta will be equal to 9W by 16 EI plus 64 minus 27. So this will be 64 minus 27 here. So you will get 64 minus 27 as this is 37, right? 37. So you will get 37. So 9 multiplied by 37W by 48 EI, right? Minus 16 minus 9, 7, 63 by 8 EI, and there is W also, right? So this we are getting. Solve it and finally you will get the answer as, so I am writing the final result now, 0.7 W by EI, 0.75 W by EI. Solving it you will get this value. W is known to us. What is W? That is 60 kilonewton divided by E. The value of E is given to us. What is the modulus of elasticity? That is given to us 2.2 multiplied by 1000 multiplied by 10 power 3. This much EI is given. So solve it and finally you will get the answer as, so solving it you will get the answer as 0.02045, 0.02045. So this is this much meters. This is the answer, right? And it can be converted to centimeter or millimeter also, for it will be, so delta will come out to be 20.45 millimeters. So this is the answer. So this is the answer of this question, right? So it's very easy to solve using the Cauchy-Lyanos theorem. We have to differentiate the strain energy with respect to the load under which we want to find out the deflection, right? So that's what we have done. First we find out the reaction in terms of W we have kept, because we have to differentiate it with respect to W. And finally finding the reactions, we have used that formula which is used for strain energy, Cauchy-Lyanos theorem, that del U by del W will be the deflection. So using that formula, finally solving it, we have divided into two parts because strain energy is taken as the total strain energy of the beam. So we have divided into two parts, 0 to 3, A to C, and from 3 to 4 meters, that is C to B, right? This divided into two parts. Put the values, we have already found out these values, put the values and finally you will get the deflection under load 60 kilonewton.